response element binding protein binding to the cyclic AMP response element is a promoter of transcription of this gene. So lots of glucagon means lots of PEP-CK, which means an increased capacity for gluconeogenesis. Right?
It promotes transcription of the PEP-CK gene.
The PEP-CK gene, which means then we make more PEP-CK, which means we increase our capacity for gluconeogenesis. So, I'll do my so later. Any questions about that? Kevin's thinking about it. Are we good?
Well, I mean, I'm guessing there's like a control way or something to like get rid of PEP-CK, where it goes away or something if you have to make it every time.
Well, every protein has a lifetime, right? A half-life. Eventually, proteins get damaged or they become detected as having been around for a while. The cell attaches a small protein called ubiquitin. And the longer a protein is around, the more ubiquitin gets put on it. And the longer that ubiquitin tail gets, the more likely it is that that protein will be recycled. So there are ways that cells determine the half-life of proteins. So, but half-life is a function of how quickly is a protein degraded and removed from the system versus how quickly is it put into the system. And so those two reach an equilibrium. So if you suddenly increase the synthesis rate, then you increase the amount of protein around at any instant. Does that make sense? And so you increase the capacity. If that glucagon signal goes away, right, eventually over time, that level of PEP-CK will drop as proteins are naturally recycled. Okay? Does that make sense? We good, Kyle? So, are we good with glucagon's effects?
One question. The catalytic and regulatory subunits, what does that make up? I forget.
Well, that's the resting state of the cyclic AMP-dependent protein kinase.
Okay.
Right? So the catalytic subunits are only active when we can tie up the regulatory subunits with cyclic AMP and free those catalytic subunits. Right? And then remember, cyclic AMP, that's an AMP. I don't know what happened to my P there. AMP. Eventually, cyclic AMP is removed from the system by the cyclic AMP phosphodiesterase. This stops. The phosphatase removes the phosphate from the protein. It stops promoting, and then we degrade the extra protein. So are we happy with the cycle to get back? Now, what's going to be my next question? What?
What do they teach you on this?
No.
Yeah.
Does it make sense that a glucagon signal would lead to that effect? Does it make sense? Why, Jordan?
Because glucagon signals low blood sugar and we want glucose.
Okay, can you say it loud enough so Jenny can hear it?
Oh. Glucagon signals low blood sugar, which makes sense. We want gluconeogenesis because we want more glucose in our body.
There we go. Right? Glucagon, signal from the pancreas that we have low blood sugar, increasing the concentration of PEP-CK, increases the capacity for gluconeogenesis, and so that does make sense. Yeah, Jordan?
Is this slide on these?
I think it is.
Can we look at it?
I do believe it is.
Definitely looks like you created it or found it.
That is definitely a created slide.
Oh, you really? Pretty good.
Yeah.
Slide.
Yeah, that is a created slide. And I did it on old ChemDraw, so I don't have it where I can edit it anymore, or I would do it and make the resolution better. Any questions about that? Does that make sense? Actually, no, I think that even predates me using ChemDraw. I think I did that on like Apple Paint or something a long time ago. Yeah.
Apple Paint.
Yeah, or Apple Draw, something on an old Mac. Claris works maybe if it was newer than that, but no, I I'd have to start all over again. So are we good with this? So now let's talk about an insulin signal. Insulin, different peptide hormone, binds to a different kind of receptor, right? Remember, the insulin receptor is an autocatalytic tyrosine kinase. That is, when insulin binds, the tyrosine kinase activity of these two beta subunits of the alpha-beta tetramer. The tyrosine kinase activity of the beta subunits is activated. The first thing they do is phosphorylate each other. So this one phosphorylates this one phosphorylates that one. That phosphorylation attracts other target proteins. At this stage, we'll just say other proteins are phosphorylated, right, as part of the insulin signaling cascade. And that cascade of phosphorylation activates something called the insulin response element binding protein, IREB. Insulin response element binding protein. Now, the insulin response element binding protein acts on a number of genes. Some it activates, some it inactivates. In this case, the activated insulin response element binding protein binds to the insulin response element, and that acts as an, what do we call it? What do you call it on genes when something inhibits, my brain locked up? There's a word. Who are my geneticists here? Right? There's an activator and an inhibitor. It inhibits transcription of the PEP-CK gene. And so insulin actively depresses the capacity to do gluconeogenesis by reducing the amount of PEP-CK we make. Because if you've got a lot of insulin around over the long term, then you're saying, I'm in a well-fed state. I'm getting sugar from other sources. Not only do I not need to waste the resources on making glucose in the liver, I don't need to waste the resources to make the enzyme needed to do gluconeogenesis in the liver. Does that make sense? And so we inhibit that. Now, let's consider the following. A 53-year-old man who drinks massive amounts of sugar-laden cola most days. What happens to that theoretical 53-year-old man's ability for his liver to do gluconeogenesis? What? Why would it go down? Again, Jenny, can't hear you.
You're drinking a lot of sugar.
You're drinking a lot of sugar, which
indicates
Makes you have insulin.
makes you have insulin,
which inhibits
the transcription of the gene. So what happens to this theoretical 53-year-old man's ability mid-afternoon to do gluconeogenesis to raise blood sugar? It's depressed. And so what does said 53-year-old man have to do in the afternoon when he starts feeling sluggish?
Drink more sugar.
Drink more sugar, right? And so it becomes this vicious feedback, right? This vicious cycle of, I would say, 20-year-old woman drinking sugary iced tea would do the same thing. No sugar? Good for you. So you're really by doing that, you're really promoting your ability to do gluconeogenesis. Because, remember, one, you're not bringing in external sugar. So you're naturally letting glucagon act. But do you remember what caffeine does?
Promotes it from not stopping that. Like it keeps the GTP and GDP going.
No, not that one. What does it do? It inhibits the cyclic AMP phosphodiesterase. caffeine directly inhibits the clearing of cyclic AMP from the system. So the caffeine in the tea keeps cyclic AMP around in the cell longer, which means this effect stays longer than it would naturally. So you actually increase your ability to do gluconeogenesis if you're drinking the unsugared tea as your regular drink instead of the high fructose corn syrup laden mega cola that is my daily drug of choice. Okay, does that make sense? So when I have a lull in the afternoon, where do I end up? When I'm out of Coke and I'm starting to feel the afternoon low blood sugar loopies.
5-hour energy.
Huh?
5-hour energy.
I do not go to 5-hour energy. Where do I go? I go to DSP's office and I hit the candy bowl. Right? How many times have you seen me in there in the candy bowl in the afternoon? Right? I set myself up. My liver doesn't react quickly enough. I start to feel tired and lethargic. I go hit the candy bowl, which just perpetuates the cycle. Right? Any questions about that? So now, let's see. Where are we? Now we are finally around the blockage. Right? So it took that to get around the pyruvate kinase irreversible reaction. But now we're back to equilibrium reactions. Phosphoenolpyruvate is in equilibrium with 2-phosphoglycerate. So if we're making lots of phosphoenolpyruvate, that can push this reaction this way. Right? If we're making lots of 2-phosphoglycerate, the 2-phosphoglycerate, 3-phosphoglycerate reaction is in equilibrium, that can push this reaction this way. Now, what did we say was going on in the mitochondrion to make NADH?
Fatty acid breakdown.
Fatty acid oxidation. In addition to making NADH in the mitochondrion, what does that fatty acid oxidation make? Starts with A. Yeah, starts with A. ATP, yeah, let's not make this too hard. So the ATP, right? ATP from the mitochondria and ATP equivalents can be transferred to the cytoplasm. So ATP, right, the high ATP from fatty acid oxidation